So in this video, we're going to look at solving exponential problems that have a base of e. So there are actually different formulas you can use for all different exponential situations. There's exponential situations of radioactive decay, and so there's a half-life formula that goes with that. There's exponential situations of population growth, so there's a formula that goes with that. And you'll see actually those formulas pop up in your textbook. But what I really love about this formula is that it works for every single situation. So this works for radioactive decay, it works for population growth, it works for like weird, awkward situations that don't fit into either of those categories. I really love this formula because it works for any exponential situation. You don't have to have specifically a half-life problem to use this formula. The other thing I really love about it is that it's just one formula instead of learning a lot of formulas for different situations. I find when you learn a whole bunch of formulas for different situations, often people forget which one do I use when, or what are the formulas in general, because I learned too many of them. So I like that about it. The last reason I love it, though, is actually that it's really handy for calculus. So I hope you take calculus next year. When you do, you'll find that when you take derivatives, which is that process of finding slopes of an exponential with a base of e, the derivatives are beautifully simple. They're actually the simplest derivative that you can do. And so having a base of e will make your calculus a lot easier than having a base of a half and some of the other weird bases that you get in the other formulas. So we're going to use this one all the time. We're going to use it for every single problem because it actually works for every problem. Okay, some things you need to know about how it works. A of t, that's the amount you have at the end. And A0 is how much you start with. So in whatever problem you're doing, we put in how much we start with here and however much we have at the end here. The only thing to watch out for with these is they have to have the same units. So A of t and A0 must have the same units. So if you see like A0 is in kilograms, A of t has to be in kilograms. If A0 is in milligrams, AT has to be in milligrams. Those have to be the same units. T is how much time has gone by. And K is the growth or decay constant. So if you have a positive K value, that means this exponential is growing. If you have a negative K value, that means the exponential function is decaying. And that's why this equation works for every situation, because a situation is either, every exponential situation anyway, is either growing or decaying, right? It's one of those two things. You just get to make K either positive or negative based on whether it's growing or decaying. A thing to watch out for with K, though, is its units. So the units of K, they have to be 1 divided by the time units. So if your units of time are, say, days, K will be 1 over days, or you might write it as days to the power of -1. If your T is measured in seconds, then K needs to be 1 over seconds, or seconds to the power of 1. So just watch out for that. All right, a little bit of background for these kinds of problems. Lots of them will involve radioactive decay. So that's the process of an unstable nucleus breaking down, often splits into a few other elements, or just a smaller nucleus and releases a particle. And that's a process that has a half-life to it. So the half-life is how much time it takes for whatever material you have to decay to half the original amount. It's a pretty intuitively named thing. So if you start with, say, 60 milligrams of something, and the half-life is 10 hours, then after 10 hours, your 60 milligrams should decay to half of that, or 30 milligrams. That's what half-life means. All right, let's try a problem. So polonium is one of these radioactive elements. It's discovered by Marie Curie. One of the other elements she discovered was radium. That's also radioactive. So let's say she takes 100 milligrams of polonium-218. She sticks it in a nuclear chamber, and the decay constant is -0.0030 seconds to the -1. So that right there is your K value. So K is that -0.0030 seconds to the -1 is another way of saying 1 over seconds. So that right there tips me off that my units of time will need to be in seconds. After 1 minute has passed, some of the polonium will have decayed into lead and then an alpha particle or more alpha particles. We want to know how much polonium is left. So we're really looking for A of t. So let's write down a few other things we know. 100 milligrams is placed in the nuclear chamber originally. That's at the beginning. So that must be A0. So A0 is the 100 milligrams. The time that's gone by is 1 minute. But be really careful there. We have to make sure our units of time and K match. So if K is in units of 1/seconds, you're going to want to convert time into seconds as well. So 1 minute, we should write that as 60 seconds. And the thing that I'm trying to solve for is how much remains. How much polonium do I have at the end? So that's A of T is what I'm looking for. My general equation is A of T equals A0 e to the K T. This is already rearranged for A0, so or A of T, so we can actually just plug in everything. So A0 is 100 milligrams, e to the K is negative 0.003 times T, which is 60. I recommend just doing this in stages, so do the top a little bit here, so do the negative 0.003 times 60, do that first. That gives you negative 0.18. And then do e to the power of that next. So remember, you'll have to use like shift ln if you have a Casio, or find wherever your e button is, and then multiply by the 100 milligrams at the end. And we get 83.53. The units of AT have to be the same as the units of A0. So A0 had units of milligrams, so I must have units of milligrams at the end here. So I have 83.53 milligrams of polonium after 1 minute has passed. All right, so phosphorus 32 is another one of those elements that decays. It has an exponential decay rate of negative 0.0486 days to the minus 1. So here K is negative 0.04861 over days is how we could write that. But I don't know how much I start with, and I'm asked to find the half-life. So this one feels like I don't have enough information, but I actually do. Start with my general equation. As always, we'll start all of these problems with this same equation. And we'll plug in the one thing we do know. So the one thing we do know is the K value. The K value is negative 0.0486. I want to find the half-life. So the half-life is how much time passes until I have half of my original amount. So if I think about it, if A0 was, say, 100 milligrams, then at half-life time, whatever that is, I don't know what half-life is right now for phosphorus, but whatever half-life time is, then A of T would have to be half of 100, right, or 50 milligrams. So if I look at what A of T divided by A0 would be, well, that would be the 50 that you have at the end divided by what you started with. 50 over 100 is a half. And notice that that's not just true of starting with 100 milligrams. That would be true if I started with anything. I can make up if I started with 20 milligrams. At half-life time, I'd have 10, and 10 over 20 would also be a half. So if I take AT divided by A0, I'll always get a half at half-life time. So I'm trying to find the half-life. I'm trying to find the time for it to take phosphorus decay to half of its original amount. It's probably a good idea to rearrange this for AT divided by A0, because what I can do is replace this AT divided by A0 with 1/2. So I can say that AT divided by A0 is actually equal to a half, and I'm going to sneak that right in there. So I'll have AT over A0 is now a half, and that equals this side, which is e to the negative 0.0486t. This is not generally true, right? This is only going to be true at the moment when the time is the half-life, and that's what I want to solve for, so that works out for us here. Now we're just solving regularly, so take ln of the half. Ln, remember, kills exponents, and that gives you down whatever the exponent is here. It kills the e here, so you get the exponent down. Ln of a half is negative 0.693. And that equals all this stuff over here. And divide both sides by the negative 0.0486. And that will give you T equals 14.26. And remember, T and K have to have these kind of connected units. So if K is in units of 1 over days, T will be in units of days. So this tells me that the half-life of polonium or phosphorus 32 is 14.26 days. All right, one more example. It looks very different, a bacteria doubling, but we can actually still use our exponential formula because this general exponential formula works for every single situation. That's what I love about it. So here we have bacteria doubling every 5 hours. We want to find the growth constant and model this as an exponential. So growth constant, that means K. We're trying to find K so that we can model this thing. So we'll start out by just kind of writing out our equation. A of T will equal A0 e to the kt. What I know is that this bacteria is doubling every 5 hours. So that means when T is equal to 5, I'll have double what I started with. Well, let's use the same trick that we used for half-life. If I think about what A of T divided by A0 is, if I start with, say, 100 milligrams, after 5 hours it will double, so I'll have 200 milligrams. 200 divided by 100 will be 2 at that doubling time. So at the moment when T is 5 hours, the amount you have now divided by the amount you start with will be 2, right? Double what you start with. So let's use that, rearrange the general equation for AT of A over A0, just like we did last time. We get this here, and then you can replace the AT over A0 with 2. So let's replace this whole side here, AT over A0 with 2. And on this side I have just e to the kt, but at the moment when AT over A0 is 2, the time has to be the doubling time, which I was told was 5 hours. So I get to plug in T equals 5. Now we're just solving normally. So I can take the ln of 2. That'll kill the e here, and I'll get just k times 5, or 5k. Ln of 2 is 0.693. That equals 5 times k. You can divide both sides by 5. And I get k is equal to 0.1386. Look back at the units of time to know what units you should have on k. So time was in hours here, so k must be in 1 divided by hours. That would be my units of k. So my general equation will be A of t is A0 e to the 0.1386 t, remembering that k has units of hours to the -1 or 1 over hours. All right, let's use that. So I'll write that equation down again because we're going to need it in a second. So A of t is A0 e to the 0.1386 t. Remember that k has units of hours to the -1. Okay, so here I'm trying to solve for how, if I start with some massive bacteria that weighs 45 milligrams, how much will I have after 7 days? So let's write down the things that I know here. A0 is how much I start with, and I start with 45 milligrams. T is how much time has passed, which is 7 days, but be careful, I need to make sure my units of T and K match. K was in units of 1 over hours, so I need to convert this to hours too. So I should convert days into hours. I multiply by 24 hours per day. That cancels the days and gives me 7 times 24, which is 168 hours. Oops, there we go. I'm trying to solve for how much I have now. So that's A of t, or A at this 168 hours. So let's plug everything in. So A0 is 45 milligrams. We have e to the 0.1386 times t in the right units, 168 hours. Start by multiplying your exponential here. So multiply those out. My exponent becomes 23.28, and then do e to the power of that. And then multiply by the 45. And we get a huge amount of bacteria. We get 5.8 times 10 to the 11 milligrams of bacteria after 7 days.